Newton's understanding of gravity was good enough to allow us to fly from the Earth to the moon. But it's kind of got to make you laugh to think that you can go all the way to the moon and back using something that's ultimately just an approximation.
It would make you chuckle to think that you could fly to the moon and back with just finite resources. Yet Newton understood gravity well enough to be able to travel from Earth to the moon. Our world is flawless in every way. There are models everywhere in the globe, yet some riddles are still unanswered after years of study. What causes the one-way flow of time? What is the reality? Why is gravity there? Why does traveling at the speed of light cause time to slow down? We have been interested by this question for millennia. Imagine that I told you that gravity isn't real. It was entirely produced by the human mind. That may sound unbelievable, but that's what renowned physician Brian Cox recently asserted. Let's examine the nature of gravity and the reasons behind the slowness of time in realizing its detrimental consequences. We have to look beyond Newton. What he cannot accomplish is the issue, not what he understands. The fact that Newton's theory of gravity only makes predictions about an object's motion under its own force is one of its flaws. Neither the existence of gravity nor its mechanism are explained by it. Newton understood that it only forces you to count. The fact that it is only from Ada is crucial. It's really stated that the sun, planets, and comets, all of nature's most exquisite creations, only function in accordance with the laws and decrees of the wise. Put otherwise, I'll provide you with the means to comprehend how things work. But don't ask me how or why. That belongs to God. The enormous cosmos we live in is full with mysteries that we have yet to solve. Some amazing phenomena pertaining to time and gravity, two essential components of our existence, are included in this list of mysteries. Imagine living in a world where time is unusual, unpredictable, and the forces that keep us anchored are not the same. This is the point at which our knowledge of time and gravity diverges from Albert Einstein's theory of relativity. The renowned Albert Einstein, whose theory of relativity opened our eyes and changed the way we understood the universe. Our knowledge of how time functions in various contexts, especially when we move at great speeds, is based on their work. It all began when Einstein postulated two crucial theories at the beginning of the 20th century: special relativity and general relativity. After its publication in 1905, the theory of special relativity altered our perception of space and time. It essentially informs us that regardless of motion, all non-accelerating observers are subject to the same set of rules of physics. Along with the well-known idea that time slows down or speeds up depending on the context, the theory also introduced the idea of social interaction. The light clock is among the most effective theories to explain time dilation. Imagine objects traveling at an amazing rate, almost the speed of light, in a spacecraft. Two mirrors in the spacecraft reflect a light beam that is perpendicular to the direction of travel. Light bounces vertically to move in a straight line, as observed from a plane. On the other hand, things seem differently to an outside observer who is not traveling with the aircraft. They followed the beam's route after seeing the fast-moving aircraft. The beam has to travel further to strike the mirror since the aircraft is in motion. The speed of light is always the same for all observers, according to the principles of physics. As a result, the beam should resemble a lengthy diagonal route. Things start to become intriguing now. Both observers within and outside the aircraft must experience the same amount of time for the beam to travel. The light takes longer to reach its destination, though, because of the lengthier travel to the outside viewer. Time dilation is the term Einstein used to describe the perceived time gap between two observers. The amount of time it takes for the observer to approach the stationary observer. Thus, in this instance, the time varies based on what you do. These trials verified the societal impact, so this is more than just a notion. Particles in particle accelerators, like the Large Hadron Collider, can, for instance, travel at almost the speed of light. Researchers need to account for the effects of time dilation in order to perform precise measurements. A universe where time is limitless and may be stretched or compressed to the strength of one's will is made possible by special relativity. It causes us to reevaluate how we normally think and realizes how much bigger than our experience the cosmos is. Proposed in 1905, Einstein's theory of special relativity revolutionized our understanding of the universe's structure, particularly with regard to time and motion. Critical theory demonstrates that, independent of velocity, all non-accelerating observers are subject to the same set of rules of physics. Let's look at the fundamentals of special relativity to have a better understanding of it. The idea that everyone experiences light traveling at the same speed, independent of velocity, is one of the cornerstones of special relativity. The speed at which light seems to travel is always the same, around 299,792,458 meters per second, regardless of your speed. This concept contradicts the common perception that motion causes us to move faster. It seems that the speed limit of the cosmos is equal to the speed of light. We think that events that happen at the same time do not happen for everyone at the same moment because of special relativity. From a different angle, what you witness happening simultaneously won't happen to someone else if two occurrences are occurring in distinct locations, and you are going towards them. This idea, which seems odd at first, contradicts how we think about time. Among the most significant and practical hypotheses is the one pertaining to time dilation. As you walk, time will either extend or slow down, as we discussed in the last section. In comparison to a stationary observer, time appears to pass more slowly while you move more quickly. The closer you go to the speed of light, the more noticeable this impact will be. Imagine you had two identical twins, one on Earth and the other traveling faster than light into space. The twins will be younger than their earthly siblings when they return. Real-time dilation is the cause of this phenomena, which is sometimes referred to as the twin paradox. The constant of the speed of light is the cause of this discrepancy. The twins saw the ticking of the clock as usual as they made their way towards it in little steps. The twin spacefaring clocks, however, seem to be slowing down to Earth watchers as they move around the globe. Length contraction is another effect of special relativity. To a stationary observer, an item moving at a fast speed seems short in the direction of motion. When objects approach the speed of light, this impact becomes more noticeable. At normal speeds, it is quite minor. E equals v/2, one of physics' most well-known equations, is a direct result of special theory of relativity. This formula demonstrates the interchangeability of mass and energy. This implies that energy and mass may be transformed into one another. Understanding this idea is crucial to comprehending how materials behave at high speeds and how energy is released during events like nuclear attacks. There is more to special relativity than meets the eye. There is information that is helpful. For instance, GPS systems depend on satellite signals being accurate. But the time dilation effect kicks in as the satellites approach us. Our navigation system will become less accurate if the impacts of specific connections are not factored into GPS computations. We are forced to reconsider how we conceive about time and space by special relativity. It demonstrates how the cosmos functions in a way that defies modernity. Time is a relative term that is impacted by movement rather than an absolute one. Two significant concepts that have been validated by numerous tests are the speed of light and the link between mass and energy. Moving on, let's discuss Albert Einstein's 1915 proposal for general relativity. This theory introduces us to the concept of gravity and shows us how the Earth's structure and gravity are related. In essence, general relativity refutes the traditional understanding of gravity as a force that depends on mass distance. Rather, it depicts gravity as spacetime's curvature. It's easier to understand than it sounds. We must consider the cosmos to be a four-dimensional object consisting of 3 dimensions of space and 1 dimension of time in order to comprehend general relativity. You may construct massive things in 4-dimensional space-time, such as planets and stars, and even bend space-time itself to accommodate them. We refer to this curvature as gravity. Consider space-time as a massive malleable construct. An item the size of the Earth would cause a break in this cloth. A ball, for example, rolls into the trenches when it is placed close to the dirt. This is comparable to what occurs when an item experiences gravity. This is only a matter of following space-time's curvature. It is not a mysterious power. A compelling explanation for the motion of celestial bodies in the solar system is offered by general relativity. It forecasts the planet's orbits with accuracy, including the elliptical route that the Earth takes around the Sun. Curved spacetime provides a more comprehensive explanation of orbital motion than the outdated theory of gravity as an attracting force. When Sir Arthur Eddington led an expedition to investigate the bending of stars due to the Sun's gravity in 1919, one of the most well-known observations of general relativity took place during the solar eclipse. According to the hypothesis, distant stars look somewhat out of position because of how the Sun's immense presence bends light from those stars' paths. The hypothesis was verified by observations made during the eclipse, which contradicted Einstein's predictions. According to special relativity, motion has an impact on time, just as gravity does. Time moves more slowly in high-gravity places than it does in weak-energy areas. This implies that your watch will run more slowly if you are standing close to a big object, like a black hole, than if you are standing farther away from the thing. The concept of the black hole, the location of the biggest challenge, was first proposed by general relativity. Nothing can escape a black hole's entry, not even light, due to its very powerful gravitational attraction. The event horizon, which denotes the edge surrounding a black hole, is the point of no return. Anything going beyond this threshold will be drawn into the black hole. The structure of the cosmos as a whole is also significantly impacted by general relativity. In order to maintain the universe's staticity, Einstein first incorporated cosmological constants into his equation. He considered the realization that the cosmos was expanding to be his worst error, though. The Big Bang hypothesis, which describes the origin of the universe, is based on the expanding universe theory, which is backed by general relativity. The presence of gravitational waves is a key component of general relativity. These are rippling effects in space-time brought on by rapidly accelerating large objects, including merging neutron stars or black holes. By directly detecting gravity waves for the first time in 2015, the Laser Interferometer Gravity Wave Observatory verified another aspect of Einstein's theory. General relativity has been put to the test several times throughout the years, and each time it has passed. This idea has been repeatedly validated by observations of gravitational waves, the bending of stars, and the actual orbits of planets. The notion that gravity is a fiction may seem startling, even paradoxical, given the way we experience gravity in our everyday lives. Nonetheless, there is always space for discussion, conjecture, and the pursuit of competing ideas in the field of physics. It is not unusual for scientists to question accepted beliefs. Several hypotheses concerning gravity contradict the conventional wisdom of this fundamental force. Their arguments center on competing ideas, some of which seek to alter or supplant our knowledge of gravity. Modified Newtonian dynamics, MOND, is another name for one of the most well-known alternative theories. It demonstrates how gravity operates differently at low acceleration than what is expected from standard Newtonian gravity. MOND argues that the behavior of galaxies does not need an appeal to darkness. Rather, MOND suggests that gravity accelerates to extremely high velocities. The primary topics of discussion in the gravity debate center on dark energy and dark matter. These enigmatic theories have been proposed to explain a number of cosmic phenomena, including the rotation and expansion of galaxies. Opponents of the standard theory of gravity contend that alternative theories adequately account for the phenomena and that dark matter and dark energy are superfluous. The idea that Einstein's theory of relativity is lacking is not shared by all experts. According to them, there could be more significant, unidentified, or potent factors at play that might alter or enhance our present comprehension of gravity. These scientists are looking at a wide range of options, including hypotheses that propose novel interactions or characteristics. It is important to note that the other idea was not given up right away. To ascertain the efficacy of these theories, the scientific community puts them through rigorous testing. Despite the fact that a number of competing ideas have received support thus far, none are thought to alter the way gravity is designed. It is crucial to stress that uncertainty and disease are significant facets of research. When pursuing knowledge, it is beneficial to challenge accepted notions and consider other options. Science is the result of inquiry and uncertainty. When the consensus of science is questioned, more research and a greater comprehension of the cosmos may result. General relativity's explanation of gravity continues to be the most significant and effective theory, despite the existence of rival and alternative theories. This is due to the fact that it is continuously put through rigorous testing and provides correct descriptions of phenomena like star bending and Earth orbits. It is challenging to modify general relativity because of its comprehensiveness and simplicity. Einstein's theory of special relativity, as we discussed, introduces the idea of time dilation, which states that the behavior of time varies with energy. Let's now investigate the practical and real-world consequences of this theory, particularly with regard to destination travel. People have long been interested in space exploration. We have aspirations of traveling to far-off planets, stars, and even galaxies. However, there are two major obstacles to traveling far beyond Earth: the size of the planet and the speed of light. The speed of light in a vacuum is the fastest speed in the cosmos, according to Einstein's hypothesis. The speed of light is the fastest thing that can travel. Because it takes a long time to reach the nearest star, even with the most modern technology, this constraint presents a significant obstacle to interstellar travel. Let's take a look at the well-known twins to better grasp what time dilation in space travel entails. Assume that one twin stays on Earth while the other travels at a speed far slower than light to a far-off star. Upon their return, the twins will discover that they have lived a shorter life than their siblings. The twins who traveled across space traveled to the future. For travelers, time is highly valuable. The amount of time dilation increases with distance traveled. Traveling to neighboring stars causes a significant time dilation effect, which may cause astronauts to age more slowly than those on Earth. Despite the fact that this seems like something out of a science fiction novel, social theory is actually to blame. Imagine a day when hefty missions are sent by humans to a neighboring star. Traveling even a small portion of the speed of light can take decades due to the distance. Time dilation will make the voyage seem shorter to the astronauts on board, but the planet they leave behind will be older. Time dilation has an impact on technology in addition to living things. For instance, in order to guarantee the accuracy and proper operation of computer systems and communications equipment on aircraft, time dilation must be adjusted. The fast-paced world of social media travel is fraught with difficulties. Individuals who operate in this capacity must take into account the consequences of prolonged seclusion, exposure to cosmic radiation, and the psychological ramifications of being cut off from Earth for extended periods of time. While space exploration to far-off stars remains a bright prospect, time dilation's impacts are already felt in day-to-day living. It depends on the precision of satellite signals to pinpoint its location, since it makes use of the Global Positioning System, GPS. Time dilation is affecting the satellites as they approach us. If social factors are not factored into GPS computations, the navigation system's accuracy will suffer significantly. Let's now investigate the idea of why time moves in a single direction. Our life and the cosmos as a whole are guided by the idea of time. Decisions made in the past, present, and future all flow from it. The core of human existence is this lonesome journey from the past to the future. Then why is there a route for time? Entropy is a notion that holds the key to understanding why time flows in a particular direction. A system's disorder or unpredictability is measured by its entropy. It has to do with the arrow of time and is a fundamental idea in physics. In other words, entropy is a measure of how much disorder or unpredictability there is in a given amount of time. The second law of thermodynamics describes the connection between entropy and the direction of time. According to this law, the overall entropy will either rise or stay the same in an isolated environment. Put otherwise, entropy does not naturally diminish, rather, it naturally tends to rise. There is entropy everywhere, and it has obvious repercussions. Consider a deck of cards that is perfectly stacked, for instance. The cards then become random and out of order if we shuffle them. The shuffled deck has a higher entropy than the initial order, which is lower. The arrow of time causes things to go from orderly to chaotic. The presence of various work hours at various life stages. At the macro level of our everyday existence, the rise in entropy is evident. By examining ice that has dissolved in water or the contents of a cup of coffee mix, we exacerbate the problem. This is a macro process that represents the one-way flow of time. The atomic and particle worlds demonstrate to us that the principles of physics are symmetrical with regard to time. This indicates that the process is inverted at the microscopic level. You won't be able to discern the difference when you play back and view the accident footage. We refer to this phenomena as time reversal symmetry. The idea of beginning circumstances gives rise to the seeming contradiction between reversibility in the microscopic world and irreversibility in the larger universe. The macroscopic universe is made up of numerous entities and their interrelationships. The arrow of time originated with the first occurrence in this intricate universe. Our brain processes information in a sequence, from previous memories to present and future expectations. This concept of a continual development of time is not exclusive to physics and the cosmos. The way we see time in the outside world is quite similar to how time actually exists. Significant concerns regarding reality are also brought up by time's one-way character. It tests our comprehension of cause and consequence and how we think. We have a tendency to view the future as limitless and the past as set in stone. These anatomical patterns influence our perceptions and conclusions. Our life is based on the fact that time exists. It contributes to our knowledge, personal development, and comprehension of the cosmos. Our world would be significantly different if time didn't exist. There won't be any results to our acts, no cause and effect to be observed.
The European Council for Nuclear Research, CERN, well known for its contributions to particle physics, is at the forefront of scientific innovation. A unique finding from the Large Hadron Collider was just made public by the renowned Particle Physics Laboratory, which has the potential to alter our understanding of the cosmos. According to scientists, this strange finding could prove that extraterrestrials live in the same universe. Experts were excited and debating this fantastic notion. Will this remarkable occurrence alter our perception of the cosmos? If yes, how does this comprehension show up? Come along as we investigate a recent finding and see how researchers at CERN shattered the taboo around a finding that might fundamentally alter our understanding of the world. Founded in the mid-1950s, CERN, as it is more often known, has gained recognition for conducting extensive experiments. Although he has received a lot of attention, his experiments have sparked worries about the potential to divide reality, create black holes, and pose several other problems. The building of the Large Hadron Collider is one of CERN's most ambitious and contentious undertakings. It is the most recent iteration of the current CERN accelerator complex, having gone into operation on September 10, 2008. It has a series of accelerators that raise the energy of particles and more than 27 kilometers of superconducting magnets. Over $4.5 billion was spent on CERN's incredible creation. Given that the LHC has produced some of the most significant discoveries of the past few decades, including the discovery of the Higgs boson and other previously undiscovered items, many people think the money was wisely spent. This enormous moneymaker has the ability to spin various items around the ring at speeds of up to 11,000 revolutions per second and the speed of light. This is accomplished by the Large Hadron Collider by employing very potent electrons in an accelerator that produces a magnetic field that is over 1,000 times stronger than that of a common magnet. Concerns have been raised on how powerful magnetic fields may affect adjacent electrical equipment, as well as the Earth's magnetic field. When two objects are driven into a violent collision, a lot of energy and difficulty are released. Objects that collide go in all directions and, for the most part, vanish quickly after impact. Searchers can locate new objects by moving an item's position. With this in mind, specialized high-security gadgets are positioned all around the accident site to gather data pertaining to every incident. This amount of data may increase quickly and takes work and time to process. Each year, these collisions yield almost 15 petabytes of raw data from LHC experiments, which are needed for the essential data analysis. The library has more than 200 petabytes of data. A petabyte is equivalent to 250,000 films. They found evidence of quark existence. As scientists point out, quarks are the fundamental building elements of matter and come in a variety of shapes. Some of these quark flavors disintegrate in the eye into other things because they are so unstable. Due to their enormous intensity, beauty quarks, with lifetimes of 1 trillionth and 2 trillionth of a second, are the focus of interest. Based on conventional assumptions, experts predicted a different degradation trend. However, there is only a 70% likelihood that quarks will decay into muons if they decay into electrons, according to data from the Large Hadron Collider. These variations are only conceivable in the event that the processes in issue have an unknown origin. Some experts have concluded that this suggests a novel application of physics may be involved. A whole new physics might be revealed by a new force-carrying particle, which could expand on the standard model and provide fascinating new insights. Model theory offers us the greatest explanation for how the universe functions, even with the possibility of new physics. The scientific foundation that explains what we know about all the characteristics of the physical universe is the standard model. Surprisingly, physicists are aware that the model is not yet complete despite its great degree of accuracy. Only 3 fundamental elements, electrical energy, strong energy, and weak energy, are described by the standard model. As of right now, neither dark matter nor gravity have an explanation. Finding findings outside this framework is not rare given the data collected by the LHC, but this time it has caught the interest of experts who think more research is necessary to establish this unique scenario. Can the surprising discovery be explained by this new power? Scientists have hypothesized the presence of a brand new energy source, an energy carrier they refer to as the Z-base. Scientists think that this force interacts with electrons and muons, despite the fact that it seems feeble and is not yet detected. Where this fits into the standard model is still a mystery, though. If verified, physicists think the finding will contribute to the explanation of long-standing riddles about the cosmos, including the nature of dark matter and the function of the Higgs boson. The unification of the fundamental energy of life is one of physics' most significant objectives of the last century, and some scientists think that this unknown energy might help achieve it. Elon claims that the European Organization for Scientific Research, led by Musk, constructed the largest and most potent particle collision in human history, the Large Hadron Collision, between 1998 and 2008. Hundreds of institutions, laboratories, and more than 10,000 researchers nationwide are contributing to this effort. It is situated in a 27-kilometer-long hole around 175 meters above the Earth, close to Geneva on the French-Swiss border. Not only that, but the LHC measured 3.5 teraelectron volts per line of energy from the initial collision, which was approximately 4 times greater than the previous world record. The energy of the beam increased to 6.5 MeV when the LHC was built further. Musk mentioned how well proton beams collide at the Large Hadron Collider. A lead ion beam can also be activated by it. Specifically, protons and lead collide for 1 month on average every year. For scientists, the primary goal of the LHC is to test the predictions of several physical theories, a broad class of particles that subatomic particle theory predicts. Similar to how the electromagnetic force holds atoms and molecules together, hadrons are subatomic particles made of quarks that are kept together by the strong force. 2 such examples are protons and neutrons. Among these is the muon meson, which was discovered for the first time in late 1940s and early 1950s during cosmic ray tests. 2 distinct streams of matter are brought together and collided at the Large Hadron Collider. The Higgs field and the Higgs boson are regarded as the most significant particles. This field is being quantum excited, just like when waves are seen in the water. From a particle quality perspective, bosons are like a completely new species. It is devoid of the carriers of quantum interactions, including the weak force, electromagnetic force, and nuclear interaction, as well as the quantum energy of basic matter. At the Large Hadron Collider, 2 massive space experiments named APLIS and CMS simultaneously made a significant discovery: the existence of the Higgs boson. The announcement was released by CERN on July 4, 2012. During that period, the new scalar boson was found in 2 uncommon decay channels that basically indicate pure decay, 2 photons that need a totally virtual process to occur and decay straight into a decay. Even though the standard model was established at the time of the Higgs boson discovery, research on the invisible boson continued. Since 2012, one of the most significant findings is the confirmation of the Higgs decay. When the 3rd cycle of the Large Hadron Collider begins in 2029, CERN predicted at the time that research into the invisible will intensify, particularly following the completion of the particle accelerator's high luminosity upgrade. This will make it possible for the LHC to carry out more collisions and provide researchers with the chance to investigate peculiar physical phenomena, such occurrences that defy the standard model. After upgrading its accelerator, CERN predicts that 15 million of these objects will be generated annually. In contrast, 3 million Higgs bosons were created in 2017 by the Large Hadron Collider. 5 other forms of Higgs bosons are predicted by particle physics theory beyond the standard model, some of which have lower production rates than the first Higgs boson. How big is the boson mass? The Higgs field plays a crucial role in the early stages of the Earth's formation. It establishes the characteristics of the emptiness that permeates our spacetime. It is in charge of the production of mass at all known fundamental levels, as well as the existence of matter and interactions as we know them. Atomic elements, stars, and life as we know it would not exist in the cosmos without the Higgs field and the Higgs boson. What makes you believe that the God particle is the Higgs boson? The phrase God particle originated with the Nobel Prize-winning scientist Leon Lederman, who furiously referred to the Higgs boson as a damn particle due to its extreme difficulty in being detected. The word gained popularity when the Higgs boson was discovered. This is the beginning of the matter and religion conundrum that still baffles modern physicists. In 1990, Lederman wrote a book about the Higgs boson and wanted to title it The Damn Particle, but the publisher disagreed and changed it to The Damn Particle. However, since only mass exists in this part of nature, it is impossible to overestimate the significance of the Higgs boson and the Higgs field. This implies that no star, planet, or individual will be able to give an explanation for his moniker. There are 2 causes. They want to know what type of space we use to live in first. Secondly, they are interested in learning how to close this gap. The transmission of non-zero neutral potential energy into space is a distinctive feature of the Higgs field. As a matter of fact, this explains every distinction in our world. The presence of an unlimited quantity of electrical energy and a little amount of weak energy is thought to be caused by the form of potential energy, according to scientists. In order to accomplish this, scientists must generate pairs of Higgs bosons in order to understand how these bosons interact. The fundamental question of how other particles in the cosmos gain their mass is addressed in part by the Higgs boson. Its vastness, nevertheless, requires an explanation. Theoretically, a loss of symmetry ensures success and causes failure. The vacuum itself can be affected by quantum fluctuations. Luckily, this measured period exceeds the known time in the globe. However, in order to boost the energy of the Higgs boson and provide the necessary new life for the body, scientists are still searching for more Higgs boson-like particles. All of these choices are in favor of the investigation into further data and, if feasible, stronger collisions. Thus, hundreds of specialists worldwide are still working on it 10 years later. First generated in 1964, the Higgs boson was found in 2012. This is a result of the massive and unstable nature of the Higgs boson. In order to produce an item of this size, scientists must focus a great deal of energy into a tiny box. They require a severe breakdown of electricity. The Higgs particle decays in a variety of ways once it is formed, and the background can only detect a small portion of it. Scientists constructed the biggest and most intricate objects to explain these things. The Higgs boson signature was later discovered by analyzing hundreds of millions of proton-proton collisions. Will it ultimately result in our demise? 3 hypotheses concerning the actual aim of CERN have been proposed by conspiracy theorists. Some people's initial negative perception of CERN is that it's attempting to open the gates of hell. Some people think that mankind will emerge from the last gates of hell thanks to CERN's experiments on subatomic particles traveling at the speed of light. However, CERN states that the goal of developing the solution is to get a deeper comprehension of the issue and its scope. According to Wikipedia, antimatter is made up of subatomic particles that function in opposition to matter. The Big Bang Theory's proponents contend that since matter was formed at the same time as the cosmos, it ought to be represented on par with matter. Yet antimatter is extremely uncommon. The Mandela effect is the occurrence where a large number of people have memories of past events that differ from their actual experiences. Conspiracy theorists predict that CERN's particle experiments would warp reality, unleash a powerful Mandela effect, and pull the planet into a parallel dimension. Conspiracy theorists contend that the European Organization for Nuclear Research location is where the human sacrifice occurred. A 2016 online video made the allegation that CERN was home to a cult. Many hooded people are purportedly seen strolling the CERN facility in the film. It is believed that the video depicts the little girl getting shot in the man's chest and face. According to The Observer, a CERN representative refuted the report, saying the event was a prank. Has the police investigation been concluded since then, is the query. It is thus not unexpected when, on July 5, 2022, scientists started working on the merger on the internet following 3 years of research and correction. This revelation will disappoint scientific fans, but it is evident that CERN has no plans to build a doorway to hell, the future, or another dimension. Travel the world swiftly. The capacity to shatter materials at very high energy has opened doors to previously unexplored parts of physics for almost 10 years. FACER, the Advanced Search Experiment Detector at the LHC, yielded surprising results. He was able to identify the first high-energy neutrinos that particle colliders created. High-precision neutrino interaction detection was achieved for 153, which is important for physical applications that will help scientists better comprehend high neutrino interactions on Earth and how radiated stars burn and transform into strange supernovae. The fusion or explosion of atomic nuclei produces neutrinos. They are produced by natural radioactivity from potassium and bananas, as well as by cosmic rays and radioactive decay in nuclear reactors and particle accelerators across the world. However, this little feeble item symbolizes the ultimate cosmic monster. When they are made, issues seldom ever arise. Per square centimeter of our body is penetrated by around 100 billion neutrinos per second, yet they are so strong that we are unable to hear them. They have been dubbed demons because of their enigmatic characteristics, and since they were first spotted flying from a nuclear reactor in 1956, scientists have been looking for them. 6 neutrinos were detected by scientists in 2021. But it took another 2 years to gather sufficient data to establish the existence of these things. Phaser specialist and CERN particle physicist James Boyd explained to us what it can teach us about deep space that other techniques cannot. These LHC low-energy neutrinos are crucial to comprehending the basic principles of astrophysics. Data will be gathered by the program until the end of 2025. With bated breath, scientists are curious as to what new findings CERN will make and how they will affect research going forward.
The European Organization for Nuclear Research, CERN, is home to scientists who are working to find an answer to history's most important issue. Ever wonder what materials make up the universe? Are you able to do this? Simply by colliding particles in a device known as the Large Hadron Collider, LHC, at extremely high speeds. The LHC can observe even the smallest particles in the cosmos, much like a massive microscope. But an odd incident happened in July of 2022. Something unexpected was picked up by the LHC as an anomaly. What was the unusual occurrence? What may that entail for us? And is there any cause for concern? All you have to do is listen through to the very end to find out. The European Organization for Nuclear Research, CERN, unveiled the world's largest particle physics experiment, the Large Hadron Collider, LHC, in 2008. This massive subterranean apparatus operates beneath the French and Swiss borders. With its ability to smash particles together at extremely high speeds, the LHC has proven to be an invaluable instrument for scientists, providing fresh insights into the fundamental elements of the cosmos. Notwithstanding its achievements, the LHC suddenly ran across an unforeseen issue. At its maximum energy, the LHC yielded an incomprehensible and mysterious result. Scientists are puzzled by this phenomenon and making assumptions about its origin and its consequences. What may this aberration signify for our comprehension of the cosmos, and why did it occur? In what ways may it impact scientific research going forward? Researchers are now attempting to find answers to these issues. An multinational collaborative vision served as the foundation for the LHC's journey. Scientists and decision-makers in Europe realized that collaboration was essential to advancing scientific research following World War II. Physicist Louis de Broglie's 1950 proposal for a common European laboratory resulted in the establishment of CERN in 1952 by 11 nations. On the French-Swiss border, CERN was founded in 1957 with an emphasis on atomic nuclei research. In the 1980s, the idea for the Large Hadron Collider, LHC, was born out of the need for a more potent instrument to unlock the secrets of matter. In 1998, a multinational team of scientists and engineers began construction. Far exceeding prior records, the LHC achieved its first particle collision by 2010 at 3.5 TeV per beam. It is now operating at 6.5 TeV per beam following many modifications. High-speed particle collisions take place at 4 distinct sites, which are observed by 7 detectors intended to record the resultant events. The LHC mostly collides proton beams, although it also concentrates on heavier ions, such as lead, once a year. Scientists may investigate hypotheses like the Higgs boson and supersymmetric particles thanks to these tests. There have been challenges along the way for the LHC, such as a significant magnet malfunction in 2008. However, it has produced important discoveries, including the 2012 discovery of the Higgs boson. With planned future modifications, the LHC, now in its third phase that will last until 2025, is primed for even more discoveries. On July 7, during its third cycle, something amazing happened. For 14 hours, a gap in Earth's magnetic field allowed solar winds to produce geomagnetic storms and breathtaking auroras. This was ascribed to a lengthy geomagnetic storm caused by a co-rotating interaction region, CIR, from the Sun. Europe lay in ruins after World War II, and scientists and decision-makers realized that cooperation would be essential to reviving science. Physicist Louis de Broglie proposed in 1950 the establishment of a common European laboratory to foster scientific progress and peaceful coexistence. The CERN Treaty was signed by 11 nations by 1952, and CERN was founded in 1957 near the French-Swiss border. Studying atomic nuclei was CERN's primary objective, necessitating the use of strong devices known as particle accelerators. By accelerating particles to almost the speed of light, these accelerators allow scientists to discover the universe's fundamental elements. The concept for the Large Hadron Collider, LHC, began to take shape in the 1980s when scientists realized they needed a more potent device to delve deeper into the secrets of matter. The LHC, which has a 27 km ring of superconducting magnets and detectors, was intended to be the biggest and most potent particle accelerator in the world. Commencing in 1998, the LHC's construction was a tremendous technical achievement. It took 10 years to complete and engaged thousands of scientists and engineers from all over the world. It was located 100 meters below the surface. The LHC was prepared to begin experiments in 2008. By burying it below ground, expenses and land area were reduced while protection from outside disturbances and the challenging Jura Mountain topography was maintained. At an energy level of 3.5 tera-electron volts, TeV, per beam, over 4 times the previous world record, the LHC produced its first particle collision in 2010. It now runs at 6.5 TeV per beam following additional enhancements. 2 particle beams are accelerated to almost light speed at the LHC and then collide. There are 4 distinct locations where these collisions occur, and 7 detectors are positioned around each to observe the phenomenon that results. The Large Hadron Collider, LHC, is an enormous scientific device used to examine the tiniest particles in the cosmos. It is comparable to a massive microscope. It runs continuously throughout the year, mostly clashing proton beams. But once a year, it concentrates on heavy ions like lead for a full month. This yearly occasion gives scientists the chance to carry out investigations into some of the most intricate and fascinating hypotheses in particle physics. Why is so much work being done? It all comes down to our innate curiosity for the cosmos and its basic elements. Testing. Hypotheses like the existence and characteristics of the Higgs boson, which was notably proven between 2009 and 2013, depends heavily on the LHC. In addition, researchers utilize the LHC to look for new particles that might be explained by supersymmetric theories and provide light on the enigmatic dark matter that makes up a large chunk of the cosmos. Hadrons, which are minuscule particles made up of even smaller particles called quarks, are the fundamental units of study at the LHC. These quarks function similarly to the protons and neutrons that make up the nucleus of an atom. The Large Hadron Collider, LHC, smashes these particles together at extremely high speeds to replicate circumstances that existed just after the Big Bang, providing a fleeting window into the early cosmos for scientists. In terms of engineering, the LHC is a masterpiece. Constructed between 1983 and 1988 within an expansive subterranean tube with a width of 3.8 meters and many concrete layers for protection, a complex of structures situated above ground beside the tunnel contains the necessary equipment for running the collider. This comprises strong compressors, cooling mechanisms, ventilation systems, and sophisticated control electronics. These components are essential to keeping the LHC operating at the forefront of scientific inquiry. The LHC's voyage has not, however, been without difficulties. Its activities were put on hold for more than a year in 2008, following a severe setback caused by a catastrophic malfunction in one of its magnets. The Higgs boson, a long-theorized but never observed particle, was discovered at the LHC in 2012, despite this setback. The particle surged back to life. This finding was a tremendous accomplishment that confirmed the validity of the standard model of particle physics and offered vital new understandings of the underlying forces governing the cosmos. The LHC restarted operations in 2015 after a number of maintenance and improvement initiatives, and it did so until 2018, when it once more went into a scheduled downtime and refurbishment phase. With a beam energy boost of 6.8 TeV, the LHC commenced its third operating phase in April 2022, with a projected duration of 2026. The European Organization for Nuclear Research, or CERN, hopes to gather even more data and produce more groundbreaking discoveries during this time. The prospects for particle physics appear bright when looking ahead. The LHC is ready to keep pushing the boundaries of what we know, from examining the nature of dark matter to examining the basic characteristics of particles and forces. Huge volumes of data are produced by each collision at the LHC, which scientists painstakingly examine using advanced detectors and computer programs. By revealing fresh information on the most fundamental interactions between matter and energy, these analyses contribute to the discovery of the universe's mysteries. This is when things really start to get exciting. The LHC generates around 15 petabytes of data annually. That's an enormous quantity of data. A global partnership established a computational grid specifically for the LHC. This network is a miracle unto itself. Finding the answers to the riddle surrounding the Higgs boson, a mystery particle, is the primary objective of the LHC. Although scientists had anticipated it, this particle had never been observed. Its large bulk made it extremely difficult to locate. Several of these Higgs bosons were intended to be produced every minute by the powerful LHC. It's similar to setting up a trap for a rare animal that has never been found but is thought to exist by many. However, the LHC went on from there. In addition to searching for the Higgs boson, it investigated other unexplored areas of physics. It looked for supersymmetric particles as well as other cosmic mysteries. It wasn't all plain sailing either. In 2008, not long after it opened, the LHC had a significant setback. Numerous collider components were harmed by a magnet problem, which caused the testing to be delayed for more than a year. However, the LHC produced several groundbreaking findings once it began to run in 2009 and 2013, including the ultimate detection of the elusive Higgs boson. Following a successful initial run, the LHC was put into slumber for maintenance. In 2015, it returned to the Internet, eager for new experiences. After a hiatus until it resumed in April 2022 with an enhanced beam energy of 6.8 TeV, its second run ran from 2015 to 2018. We will be enthralled by this machine's third run until 2026. However, on its third run on July 7, something remarkable occurred. Consider the magnetic field of Earth as a bubble that protects our planet. That day, this bubble developed an enigmatic fracture. It was not only a temporary error, it was operational for an astounding 14 hours. Imagine the sun as a powerful river that is continuously gushing energy. The sun occasionally releases strong energy bursts that resemble river rapids. Similar to when two rivers combine to make an amazing waterfall, these bursts cause brilliant light displays known as auroras to appear when they strike Earth. One of these bursts hit with Earth's magnetic field during the peaceful early hours of July 7, leaving a persistent tempest of lights in the sky. Because this storm was preceded by another solar flare, scientists from the National Oceanic and Atmospheric Administration, NOAA, observed that it was significantly stronger. Should these occurrences worry us? Not really. Like a strong shield, Earth's magnetic field often withstands periodic outbursts. There could be cracks, but they usually mend fast. But as recent events have demonstrated, these fractures can occasionally persist for hours, much like a window that refuses to close after a storm. A little amount of the storm's energy still gets through even if the majority of it is blocked. Our electrical systems, radios, and satellites may all be affected by this. Don't worry, though, although these disturbances might be annoying, they can also bring forth breathtaking surprises, like as the breathtaking northern lights that Americans and Canadians have been witnessing during this celestial event. Scientists have found that the sun is more active than they had predicted, which indicates that we will be receiving more frequent radiation bursts. Thus, you're in luck if you've ever desired to view an aurora. The likelihood of seeing this amazing natural spectacle within the next 3 years is higher than ever. It appears as though the heavens are preparing for a spectacular color dance, brought forth by our energetic Sunday. Uncovering the mysteries of the Higgs boson was one of the astounding findings achieved by the LHC in July 2017. By the year 2021, it has discovered 59 new hadron particles. Subsequently, in July 2022, it detected an entirely new particle composed of a distinct mixture of quarks, known as the pentaquark. However, even the much-loved LHC has problems. Its capacity to provide groundbreaking discoveries may diminish over time. That is the role of updates. As of June 2018, it is receiving a substantial upgrade known as the high-luminosity Large Hadron Collider. This upgrade will supercharge the LHC, increasing its capacity to detect uncommon cosmic events. For what is the LHC renowned? Well, it found the elusive Higgs boson on its maiden run. We have learned even more about this particle from the second run. Now that the third cycle is scheduled to conclude in 2025, CERN scientists anticipate having twice as much data and maybe twice as many discoveries by 2029. Particles will be colliding at 10 times the speed of light at the LHC after extensive preparation. However, the fun doesn't end there. 10 times greater data sets than what will be available at the end of its third run will be gathered during this phase, which is anticipated to last until 2042. Let's now discuss proton collisions. Protons can be thought of as multicolored jelly bean sacks. Smaller particles known as quarks are contained inside these bags and are kept together by even smaller particles known as gluons. Most of the time, jelly beans disperse when 2 bags of them crash against one another. However, occasionally a head-on collision between 2 quarks or gluons causes all of their energy to condense into a single point before exploding. The problem with the LHC is that protons collide at an astounding 40 million collisions per second. Imagine attempting to freeze a special moment from an endless fireworks display, where every shot produces a picture that is 20 times larger than what you could photograph with your phone. Similar to attempting to locate a needle in a haystack. So how do scientists make sense of all this information? Like a careful photographer selecting the best photographs, a clever computer system only chooses the most interesting encounters. These are the times that scientists examine thereafter in an effort to solve the greatest mysteries of the cosmos. The current primary goal of the LHC is to find previously unseen subatomic particles that may hold the key to unlocking new cosmic riddles. Some of these particles break down into smaller particles with enormous energy, like champion boxers. They are the super heavyweights of the cosmos. On the other hand, these heavyweight particles might not be directly detected by scientists during the third run of the LHC. Rather of focusing on locating the actual wealth, they aim to spot hints or glances, similar to discovering a map during a treasure hunt. These indications may open the door to more significant findings in upcoming runs. Dark matter now enters the picture. That strange material that is mostly invisible yet makes up our cosmos is definitely something you've heard of. Although they are so elusive that they seldom manifest themselves directly, certain new particles found at the LHC may have some connection to dark matter. It's similar to attempting to see the wind, although you can't, you may perceive its effects, such as the rustling of leaves. Scientists search for additional particles that travel abnormally at the LHC, which might indicate the existence of these unseen particles. But it's hard to find these subtle indicators. It's like trying to hear a whisper at a rock concert. Upgrades to detectors are underway for Run 3 of the LHC to improve their ability to detect these tiny clues. But there's still more. A larger device, called the Future Circular Collider, is being planned. Consider it the larger brother of the LHC, a colossal particle smasher with a potential price tag of $21 billion to $9 billion. Not everyone, though, concurs with this notion. Some contend that considering the enormous cost, we need to look at other ambitious scientific endeavors, such as building a massive radio telescope on the moon's far side or putting a space-based gravitational wave detector in orbit. Famous physicist Sabine Hossenfelder wonders if the secrets we're seeking to learn will be revealed by this new enormous machine. It's comparable to purchasing a powerful telescope that might not reveal any new stars. The LHC is getting ready for a third and maybe a fourth run in spite of this controversy. We have the impression that we are gradually revealing more and more hints, much as in a cosmic detective thriller. Additional insights into the underlying principles of our universe are promised at every step. Consider scientific discoveries to be like exciting TV shows with new and unexpected revelations about the cosmos at each turn.
Some of the most important discoveries in contemporary history have been made possible by CERN, the most sophisticated scientific research facility in the world. What if I told you, though, that there's something far worse going on beyond those closed doors? Today, we're delving into the startling assertions made by none other than David Icke, who feels that CERN experiments are endangering not just science, but all humankind. Prepare yourself, for what you are about to hear may permanently alter your perspective on the world. The goal of CERN is to discover the mysteries of the cosmos. The research done here is nothing short of groundbreaking, ranging from the discovery of the Higgs boson to investigations into the fundamental structure of space and time. However, enormous power also entails immense responsibility, or in this instance, significant risk. Since its founding in the middle of the 1950s, the European Council for Nuclear Research, more popularly known as CERN, has gained recognition for its audacious experiments. Its revolutionary work has garnered much attention throughout the years, both favorable and bad. Some of its tests, meanwhile, have sparked concerns about possible hazards, including the creation of black holes or the disruption of reality. Upon its completion and operation on September 10, 2008, the Large Hadron Collider, LHC, became one of CERN's most renowned and controversial undertakings. The world's biggest particle accelerator, this enormous device spans over 27 kilometers and is outfitted with strong superconducting magnets. Particles are propelled to extraordinarily high energy as they speed through its tunnels by a number of accelerating devices. Even with its high price tag of more than $4.5 billion, many contend that the investment paid off. After all, the Higgs boson and many other hitherto unidentified particles have been identified, and the LHC has produced some of the most revolutionary discoveries in recent memory. Envision this: enormous apparatus propelling particles around its enormous loop at velocities nearly equal to the speed of light, doing more than 11,000 laps every second. It's a miracle of engineering and human intellect that opens doors to hitherto unreachable knowledge domains. The LHC generates a magnetic field within the accelerator that is almost 1,000 times greater than the Earth's magnetic field, using a number of strong electromagnets. When particles approach their maximum speed, nearly the speed of light, some are concerned about how this strong magnetic field can impact surrounding devices and possibly the Earth's magnetic field. These incredibly fast particles clash head-on, ejecting a burst of energy and other particles. The majority of the particles disappear in these fast collisions, few seconds at most. To catch every detail of these brief occurrences, scientists deploy specialized detectors surrounding the impact spots. It takes a lot of time and effort to sift through the enormous quantity of data produced by these collisions, more than 15 petabytes annually. An important milestone was accomplished in 2017 when the LHC stored more than 200 petabytes of data, or over 250,000 movies. But what precisely are academics seeking to find among all this data? Scientists observed an oddity involving a certain kind of quark. Small particles known as quarks comprise everything in our environment. They are available in a variety of forms, such as ice cream flavors, some of which are highly unstable and rapidly transform into other particles. They were interested in the beauty quark because of its extremely short half-life, which is only a fraction of a second. Beautiful quarks should normally decay into leptons, which are lighter particles that can be either an electron or a muon. Scientists had assumed that each would have an equal chance of occurring, but data from the Large Hadron Collider revealed something different. Approximately 70% of these quarks were becoming muons instead of dividing equally between electrons and muons. This anomaly points to a potential hidden participant in the equation, a strange particle that hasn't been observed by scientists previously. It's similar like discovering a missing piece from a puzzle you believe to be complete. Now, some scientists are questioning if this would indicate the existence of a completely new set of laws governing particle interactions, upending the physics community's accepted standard model. It's a fascinating idea that could provide answers to a lot of unanswered concerns regarding the cosmos. Discovering new physics is more ambitious than what the standard model can explain at this time. This model describes the behavior of minuscule particles in our environment, much like a blueprint. It contains almost everything known about the tiniest building components of nature, which makes it amazing. Despite its extreme precision, experts believe it to be incomplete. The strong force, the weak force, and electromagnetic are the three primary forces discussed in the standard model. However, it makes no mention of dark matter or gravity, the enigmatic substance that comprises the majority of the cosmos. Thus, during recent studies, scientists observed an oddity in their data. The data did not fit the predictions of the standard model. Strange outcomes are not unheard of, particularly given the volume of data coming from experiments such as the LHC. Yet this time, scientists became interested. They began to delve further in an attempt to ascertain what was happening. Their concept? Perhaps something quite else is at work here. It was dubbed Z-prime, and it could be transported via a brand new class of particle. Since there have been no prior indications of this force, it may be quite weak, but it might still account for this surprising finding. Though they are unsure of how this new force might interact with known conventional particles, the researchers believe it would behave differently with electrons and muons. It would be extremely significant for physics if researchers discovered new particles that carried this force. If this discovery is confirmed, physicists believe it will contribute to the resolution of major cosmic mysteries and provide an explanation for long-standing questions regarding dark matter and the function of the Higgs boson. It is thought by some scientists that this new force might play a major role in the unification of all fundamental forces in physics. Elon Musk claims that between 1998 and 2008, CERN built the largest and most potent particle collision in history, known as the Large Hadron Collider. Over 10,000 scientists contributed, in addition to several organizations and laboratories from more than 100 nations. It is located around 175 meters below the surface in a 27-kilometer tunnel that runs beneath the French-Swiss border close to Geneva. With an energy of 3.5 tera-electron-volts per beam, the first collision ever observed at the Large Hadron Collider was 4 times more powerful than the previous record. After the modifications were made, the energy in the Large Hadron Collider shot up to an astounding 6.5 tera-electron-volts per beam. Musk said that this enormous device is specialized in precisely smashing proton beams together. Interestingly, it can also shoot lead-ion beams, an accomplishment that happens once a year for a certain month. In order to confirm or refute the predictions of various particle physics theories, experts closely examine them during these sessions. The discovery of new particles predicted by subatomic theories and the puzzle of the nature of the Higgs boson are central to the purpose of the Large Hadron Collider. At this size, hadrons are the fundamental units of matter. They are complex structures made up of quarks joined by a strong force akin to the adhesive that holds atoms and molecules together. Protons and neutrons are well-known hadrons, but there are also less well-known ones like pions and kaons, whose existence was discovered in the middle of the 20th century by cosmic ray investigations. By bringing two opposing particle streams together, the LHC orchestrates a massive cosmic collision that makes it easier to investigate the elusive Higgs boson. Like waves in the water, this boson is an elementary particle entangled with the Higgs field. It appears as a ripple in the quantum sea. It is a new addition to the ever-growing collection of particles, apart from fundamental matter and without the quantum characteristics of carriers of fundamental forces like as nuclear interactions, the weak force, and electromagnetism. At the enormous research facility known as the Large Hadron Collider, the Higgs boson was found. This groundbreaking accomplishment occurred concurrently with experiments carried out by ATLAS and CMS, two significant teams. The revelation was announced on July 4, 2012, at the prestigious scientific facility CERN. The two most unusual decay pathways yielded the strongest signs for the Higgs boson detection at first. These decay routes included the particle either immediately converting into a pair of Z bosons, particles that provide a basic force in nature, or directly breaking down into a pair of photons, a process that is solely controlled by quantum mechanics. The Higgs boson's discovery did not, however, signal the end of scientific research. Instead, it sparked more research. The confirmation of the decay mechanism of the Higgs boson has been one of the most important discoveries since 2012. Leading this study, CERN predicts that searches for this elusive particle will be becoming more intense, especially in the third operating phase of the LHC. The high luminosity improvement, which is scheduled for completion in 2029, will drive this phase. With this improvement, the LHC will be able to perform more collisions, giving researchers more chances to find events that go beyond the assumptions of particle physics standard model. After the accelerator is updated, CERN predicts that it will create an astonishing 50 to 15 million Higgs bosons yearly, which is a significant increase over the 3 million that were produced in 2017. This production spike may be very helpful in differentiating between different Higgs boson forms. Up to 5 other variants of the Higgs boson are postulated by theories outside of the standard model. Some of these forms could be less commonly detected than the basic type. However, what's the big deal about the Higgs boson? The Higgs field plays a key role, particularly in the early cosmos. It creates the vacuum in which everything exists and determines the nature of space. Without it, the cosmos wouldn't contain mass in its minuscule building pieces, and there wouldn't be matter or the substance that holds everything together. The fundamental components of atoms, stars, and even life itself would not exist if the Higgs field and its particle, the Higgs boson, were non-existent. Because it was so difficult to locate, the Higgs boson came to be known as the God particle. Because it was so difficult to detect, a scientist by the name of Leon Lederman jokingly dubbed it the goddamn particle before the moniker became well known owing to the media. Despite some controversy between science and religion, the Higgs boson and its field are significant. He planned to refer to it as the goddamn particle in his book, but his publishers changed it to the God particle. They are necessary for everything to have mass. Without them, there would be no stars, planets, or even humans. There are 2 primary reasons why researchers are exploring the properties of the Higgs boson. First and foremost, they are eager to learn more about the early phases of the cosmos and the origins of the physical vacuum that surrounds our world. Their second area of concern is the mechanism by which this vacuum can continue to be stable throughout time. One unusual characteristic of the Higgs field is that it contains a potential energy that is always present and affects the physical vacuum. This distinct quality is essential to the formation of the cosmos as we know it. Researchers think that by comprehending and using this energy potential, basic forces like the weak force, which works over incredibly tiny distances, and electromagnetism, which spans eternally, may be explained. Scientists need to investigate the interactions between Higgs bosons in order to uncover these mysteries. To do this, pairs of these elusive particles must be created. Although the Higgs boson has shed light on how other particles get mass, its own mass is still unknown. Its mass cannot be guaranteed by theoretical symmetry, which might result in instabilities that cause quantum fluctuations to disturb the physical vacuum. Luckily, these disturbances occur over a longer period than the universe's known lifespan. Still, the search goes on. In order to stabilize the Higgs boson mass, scientists are searching for new particles that resemble Higgs particles. This quest fuels the need for deeper data analysis and, if feasible, access to colliders with greater energies. As a result, 10 years later, hundreds of committed specialists throughout the globe continue to work towards solving these puzzles. The mysterious particle known as the Higgs boson, which was initially proposed in 1964 and was only confirmed in 2012, has baffled scientists with its slow discovery. This delay is caused by the large mass and short lifetime of the Higgs boson. High-energy colliders were required in order to compress enormous quantities of energy into a small area in order to create such a large particle. After they develop, Higgs particles break up quickly into many pieces, only some of which can be distinguished from the background noise. Scientists built massive and complex detectors to identify these elusive particles, sorting through billions upon billions of proton collisions in search of the distinctive signatures of a Higgs boson. Conspiracy theories, however, are rampant among the scientific frenzies surrounding CERN's discoveries. There are many who cast doubt on CERN's genuine objectives, speculating that its experiments may open a portal to otherworldly domains. They worry that CERN may unintentionally unleash forces beyond human comprehension by manipulating subatomic particles at speeds that are unthinkable, plunging mankind into an apocalyptic state. CERN fiercely disputes such allegations, claiming that their search for antimatter seeks to further our understanding of the cosmos rather than call in the devils. In cosmological theories such as the Big Bang, antimatter, particles that have opposite electrical charges to ordinary matter, is thought to have been a crucial component in the origin of the universe. Instead than pursuing disaster, CERN's research projects aim to shed light on the riddles of life and get them one step closer to discovering the universe's secrets. The world's biggest particle physics laboratory, CERN, has a unique place in scientific fascination for antimatter, despite its rarity. The Mandela effect is a further intriguing concept that has drawn notice. This phenomenon explains the ways in which communal memory and real events might diverge. According to some theories, CERN experiments might cause broad differences in our memories, akin to the Mandela effect, and could even propel us into alternative realms. Conspiracy theorists have also been hearing rumblings of dark operations at CERN, including claims of human sacrifice. In 2016, a smuggled video supposedly captured hooded individuals performing a ritual, including graphic visuals of a kid suffering. CERN, however, quickly disregarded these allegations, claiming it was a manufactured joke. It's unclear if officials looked into this matter further. With its cutting-edge research and enigmatic atmosphere, CERN is a magnet for conspiracy theories. Online speculation spiked again in July 2022 when scientists reopened after significant renovations. In the middle of all the drama, it's important to remember that CERN's endeavors are based on science and are not the stuff of gloomy predictions. Rather of creating gateways to other worlds, CERN's investigations examine previously undiscovered physics while delving into the fundamental secrets of the cosmos. A startling discovery has been found by the Large Hadron Collider's Forward Search Experiment detector. It has detected high-energy neutrinos produced by a particle collider for the first time. It detected 153 neutrino interactions with astounding accuracy, which is a noteworthy accomplishment in particle physics. This discovery clarifies the enigmatic processes of star burning and supernova explosions and opens doors to a fuller understanding of the tremendous neutrino interactions across the cosmos. It's critical to acknowledge the enormous influence that CERN has had on our comprehension of the cosmos, especially as scientists anxiously await more disclosures from this organization. Experiments at CERN continuously test our fundamental understanding of physics and push the frontiers of human knowledge, from discovering the Higgs boson to locating elusive neutrinos. CERN's quest for knowledge is not without controversy, though. Some people believe its experiments are linked to malevolent operations or fear cataclysmic outcomes. Despite these reservations, the organization's dedication to expanding scientific knowledge for the sake of humanity is shown by professional debunking and scientific reassurance. In fact, CERN's efforts not only deepen our understanding of the cosmos, but also spur technological advancement and motivate scientists of the future as they consider the seemingly endless possibilities that lie ahead. Future findings from CERN have the potential to alter our understanding of the cosmos. CERN is at the forefront of research into the nature of spacetime, the mysteries of dark matter, and the fundamental forces of the cosmos. We are excited about CERN's amazing achievements and how they have increased our understanding of the cosmos, and we can't wait to see what else it will unveil. When we investigate the universe with CERN, who knows what groundbreaking discoveries are ahead? It's an exhilarating adventure, full of the excitement of learning new things and going beyond our preconceived notions of what is possible. We are getting closer to discovering the mysteries of the cosmos and comprehending reality itself with every experiment conducted at CERN. Findings that might fundamentally alter our understanding of the cosmos are made possible by the complex operations of the Large Hadron Collider and the meticulous data analysis performed by experts. In addition, the spirit of adventure that CERN embodies serves as an inspiration to scientists, educators, and enthusiasts throughout the globe. It highlights how vital it is to explore out of pure curiosity and seek information for the sake of humankind. These little subatomic particles, known as neutrinos, are produced by a variety of atomic processes, including nuclear reactions, cosmic rays, and even the radioactivity of bananas and potassium. Although they are abundant, they are nevertheless elusive, which has led scientists to refer to them as ghost particles. Scientists have been pursuing these elusive particles ever since they were discovered in 1956. 6 neutrinos were found in 2021, but it took another 2 years for scientists to properly prove their existence. Co-spokesperson for the project, James Boyd, a particle physicist at CERN, claims that research on these spectral particles can offer novel insights into deep space that cannot be obtained through other means. For particle astrophysics to progress, the search for neutrinos at the LHC is essential. Scientists hope to discover more of these spectral neutrinos and solve unsolved physics problems by collecting data through 2025. The scientific world is anticipating CERN's next revelations with great anticipation as they consider the significance of these discoveries for science's future.
Unexpected occurrences have led to the release of startling information on CERN and its enigmatic Large Hadron Collider, which is both the scientific emblem of God and the means by which the cosmos has been formed. Although this was written off as a web of conspiracy and debate, recent information from CERN authorities raises the possibility that some of these allegations are genuine. In fact, a number of the alarming aspects caught the public off guard, and many demanded that the new endeavor be discontinued. Why is there a problem with the Large Hadron Collider? What is ahead for our planet as a whole, and for this monumental scientific endeavor? Come along as scientists from CERN claim to have unlocked a doorway to a parallel realm. The Large Hadron Collider is unique among scientific equipment and developments, either in terms of its aim or category. The pride and happiness of modern scientists comes from this heritage, which is the largest and most potent particle collider in the world. Nestled beneath the French-Swiss border in the verdant setting of Geneva, this impressive location is the gateway to discovering the vast and fascinating subatomic realm. The construction of giant science merry-go-round, which is 100 meters above the Earth, took 10 years and involved the cooperation of hundreds of scientists and specialists from all over the world. The world's first Large Hadron Collider was created as a result of Einstein and Faraday's commitment and sacrifice. The collider smashes atomic particles in a controlled setting with the sole goal of studying quantum particles instantaneously. the scientific community was able to create collisions with energy of up to 3.5 teraelectronvolts per line in 2010 thanks to the Large Hadron Collider, LHC. The voltage is around 6.5 teraelectronvolts each beep. According to the most recent data from the LHC, while this may seem like a little figure to the general public, it is startling to the ordinary physicist. To put it more precisely, moving at the speed of light requires 6.5 teraelectronvolts of energy. The LHC material will blow up if an energy block of some kind is present. The explosions produced by collisions at the Large Hadron Collider produce an incredible shower of large particles that is unobtainable from any other accelerator. With the exception of a few detectors at the Large Hadron Collider, it is currently difficult to follow these particles as they are going in all directions. Every year, the LHC's experiments generate almost 15 petabytes of raw data. You may appreciate the magnitude of the material CERN must sort through each time the LHC fires by keeping in mind that 1 petabyte is equivalent to 1,000 terabytes. While a great deal of public worry and discontent has been directed at the LHC experiments, CERN has made it abundantly evident that this research is both necessary and vital. Impact patterns and collisions at the Large Hadron Collider, as well as in the invisible subatomic realm, happen on a daily basis, according to CERN. Since this is being done in a controlled atmosphere, there should be no danger if the scenario is repeated. As you are aware, scientists have long harbored the desire to strike things at speeds approaching the speed of light. A portion of the kinetic energy of a collision between two protons can be transformed into mass. Furthermore, new elements may be made into something new by combining them with their counterparts. The possibilities are unlimited since these new particles can merge with already existing particles by crashing protons to form new ones. Closing the door on the enormous potential for scientific discovery would be equivalent to shutting down the Large Hadron Collider. When you consider the uncertainties surrounding the current standard model of particle physics, you can see why CERN chose to start operating the Large Hadron Collider. Unbeknownst to many, the Large Hadron Collider is capable of much more than just pushing things into odd positions. In reality, scientists may investigate the predictions of several particle physics theories thanks to this special study tool. Additionally, strong ion beams can be produced by the Large Hadron Collider to explore hitherto unexplored regions of particle physics. CERN researchers are highly intrigued about this discovery because of its enormous potential. The enthusiasm culminated in 2017 when the Large Hadron Collider produced an unexpected discovery that humiliated the sub-collider's detractors and sent shockwaves across the scientific world. The Higgs boson has been discovered. See, in 2017, the boson particle, or Higgs boson, was finally found by the Large Hadron Collider, fulfilling a long-held hypothesis in particle physics. Higgs particle or God particle are two of the numerous names for this particle. Still, it is a crucial component in the paradigm of particle physics. Scientists claim that bosons are the essential building blocks of the Higgs field, which imparts mass to all other fundamental particles, including quarks and electrons. The scientific world has long argued whether or not such a thing exists. Boson particles have not been detected in reality, hence the majority of the knowledge regarding them is theoretical in nature. You can only imagine how happy CERN scientists were to finally announce that boson particles had been found at the Large Hadron Collider. We credit the European Organization for Nuclear Research's, CERN, entails and CNS experiments for this significant finding. Along with many additional observations and direct decay of a double Z boson, scientists have found strong evidence for the existence of the Higgs boson particle. Nevertheless, there is not much time to thoroughly examine the Higgs particle because of its fast degeneracy. Even if the Higgs theory and the boson particle's existence have been verified, there is still a great deal we don't know about the uncertainty. Consequently, CERN remains dissatisfied with this explosion. Actually, the organization is attempting to descend into mystery like a rabbit hole and finally solve all of the riddle's hidden facts. Currently, CERN physicists are searching for methods to quantify the characteristics of the Higgs boson and particles associated with it. This desire will come true thanks to upgrades like the high luminosity upgrade, which the LHC just revealed, making the facility a more potent device. Here, brightness is a straightforward measure of accelerator particle activity that is correlated with the quantity of collisions that take place over time. By converting the LHC to a high luminosity LHC, more data will be produced to observe uncommon phenomena and greater collisions will be possible. Perhaps this time, researchers will uncover more enigmatic boson particles like fermions, hadrons, and gluons. Similar to how atoms and molecules are bound together by the electromagnetic force. Hadrons are subatomic composite particles composed of quarks held together by the strong force. Mesons and baryons are the two categories of hadrons. Mesons are made up of one quark and one antiquark, whereas baryons are made up of 3 quarks. This categorization is based on the quantity of quarks present. A type of basic particles known as fermions adheres to Fermi-Dirac statistics. Quarks, neutrinos, and electrons are also among these particles. While all of these fascinating facets of particle physics will be thoroughly explored, the primary focus will be on the idea of the Higgs boson outside of the context of particle physics standard model. Predicts the existence of 5 distinct Higgs boson kinds. The majority of objects created by LHC experiments are transient, which is a major challenge that CERN specialists are currently working to overcome despite the LHC's unrealized potential. A fraction of a second is all that certain particles have before they collapse into smaller ones. Interestingly, even when all particle detectors are located in one location, some particles remain undetected. This is a drawback when studying some subjects since it is impossible to examine them for brief periods of time in their stable condition. Researchers are currently considering ways to maintain these objects in a stable condition and further their scientific endeavors. The fundamental motivation behind the discussions about constructing more particle accelerators beyond the Large Hadron Collider is likewise this enigmatic state of affairs. CERN will be able to examine the subatomic realm with greater accuracy than previously thanks to its new high luminosity LHC. However, there was a lot of disagreement and public alarm as word spread of a larger, more complicated tragedy. Tales about the LHC's impending demise continue to spread throughout the globe, and many individuals are still advocating for its closure. Since the announcement of the Large Hadron Collider by CERN many years ago, there have been several fears among the scientific community. Many are concerned that the collider's billions of subatomic collisions would surprise them. It can be risky for many scientists to smash numerous particles apart at the speed of light, particularly when you have no control over what will be created in the collision. Certain specialists maintain that natural subatomic collisions vary entirely from artificial collisions at CERN and are part of a distinct process. Nevertheless, other experts suggested that something sinister and enigmatic, something perilous and dangerous, might be at play despite the surprise. Many academics have expressed concern about this unsettling notion, which holds that CERN may be able to establish a link to another place. If you enjoy science fiction, you are probably aware of the numerous ideas that contend that there are numerous parallel universes with subtle differences and similarities that exist alongside our own. According to the hypothesis, there will be an endless number of universes, each with a unique population of stars, galaxies, and even sentient species. The inflation hypothesis, which was developed after the Big Bang, when the cosmos quickly expanded and grew greater than it had been previously, lends more credence to this concept. According to certain theories, inflation will stop in this planet, but will still produce other ones. Many people hold this hypothesis to be true, despite its disagreement in the scientific world. This is especially true in light of several horrible occurrences that have occurred recently, such as the Mandela effect. The phenomenon known as the Mandela effect occurs when several people mistakenly recall the same object or event. Over the years, several amazing examples depicting this phenomena have been documented, and new ones appear each. The fact that this event is taking place globally is what makes it so amazing. This begs a few questions, including what triggers the Mandela effect? What impact does it have on people globally? The Mandela effect began shortly after CERN constructed the Large Hadron Collider in 2008, which is one of its ironic aspects. Reported by Fiona Broome, a woman. Though he got out of prison, ran for president, and passed away 2013, he thought Nelson Mandela had died in prison in 1980. That Rye had the same recollection perplexed him. He started to feel lightheaded when more research indicated he wasn't insane. However, the question of why or what makes this odd remains unanswered. That is, until some hoaxers began pointing the finger to CERN. These ideas hold that the 2008 construction of the Large Hadron Collider at CERN disrupted the structure of the cosmos and restored equilibrium. The hypothesis further clarifies that the erroneous recollections that people experiencing the Mandela effect claim to have are memories of our previous reality. While this may come as a surprise, several informed individuals have stated a comparable reality. Professor of Science Max Laughlin is one of the most ardent supporters of this idea. Laughlin recounted some of the miracles that people have thought about CERN since she, at the age of 13, said that CERN erupted into our world and brought us into balance. Machines that take the world by surprise. Laughlin won over hundreds of people to his way of thinking through his followers. Furthermore, scientist Stephen Hawking cautioned throughout his life that tampering with God's word might ultimately result in the destruction of our planet. Because of all of this, a lot of common people and science enthusiasts worldwide are wondering if CERN erred when it destroyed our planet in the pursuit of finding particles and exploring the quantum realm. A few prominent conspirators even charged the group with purposefully leaving the door open in secret. Some claim that these portals serve as entrances to other realms as well as interdimensional portals inside our own. There is conjecture as to who or what enters our world through these portals, from ghosts to aliens to fairy tales. Many people are curious in CERN's Large Hadron Collider and the amazing concept of opening a doorway to weird, unknown dimensions. In an effort to find a more effective approach to move the company forward, CERN is now illuminating the next generation of scientific findings while continuing to offer these new discoveries to the public and media. However, because the public and certain elites were preoccupied with gloomy issues, the organization was unable to take any action. An increasing number of individuals draw attention to CERN and its unexplained disaster each year, which sparks debate and events for them. For instance, there have been rumors that the 2016 earthquake in Italy was caused by the Large Hadron Collider. There is a rumor that a high voltage was sent into an Italian laboratory 250 miles distant by the Large Hadron Collider. He continued by saying that CERN purposefully raised this blood pressure in order to open a doorway to another realm. The fact that this assertion originated from a reliable source rather than some random person with a social media account contributed to its rapid dissemination of information. Although CERN refuted the accusations right away, the public's interest persisted. Locals soon started talking about the enigmatic storms and weather that passed over the LHC during its enigmatic functioning. Images of this storm have already circulated widely on the internet, leading many to conclude that CERN had unlocked a strange door. But as CERN conducted scientific tests, one of the most bizarre and unsettling incidents of that year put the organization in grave danger. There was a potential murder mystery just in front of the movie theater. In the 1-minute clip, A woman can be seen in the center of a group of males wearing hoodies and dressed in black who are standing in front of the Narrage monument inside the CERN building. Following a brief exchange of sluggish and peculiar motions, the woman was pushed to the ground and fatally stabbed. After the unsettling photos went viral on the internet, people quickly began criticizing CERN and posing questions. But according to the media, official organizations and spy services like the European Organization for Scientific Research, CERN, this was a fake and inexpensive performance put on by certain persons. However, the crowd thought quite differently. In fact, there are hints throughout the movie that point to this horrifying incident as a CERN theater production. The fact that the black perpetrators of this heinous crime wore it around their necks first revealed that they were actual laborers. The movie's lack of actual location shooting is another issue. Up until the woman was stabbed, the man filming the scene hid in a tall building nearby and said nothing. The man turned over in fright at this point, gasping in shock. This man went somewhere nobody expected to go and encountered something terrifying and unexpected. It's a common opinion among Ninas that the pictures shot lack context. This happened at night, in complete darkness, and with no background noise. Furthermore, CERN facilities are more than simply a public performance space. Therefore, who would have the audacity to hold such a demonstration within a government establishment? What's more, why was the murderer able to get into CERN? By labeling it a fraud, on the other hand, the organization is being religious and obviously trying to hide its tracks. However, the message being transmitted at this time is not odd. Many people speculated that the passenger automobile had crashed following its 2008 introduction, believing it had arrived from the future with the intention of causing harm. In addition, there was a rumor that travelers had harmed the magnet, which led to the experiment's final cancellation. It's a rumor, but you can't help but wonder whether the general concern that the Large Hadron Collider will rupture space-time has materialized already. Astronomers have just discovered fractures in Earth's magnetic, and once more, fingers are crossed at CERN. It is one thing to formulate a hypothesis. It is quite another to prove it. These massive conspiracy ideas and charges cannot hold up in the absence of solid proof. Therefore, CERN cannot assume any blame for any of the difficulties described unless more proof proves any or all of the plots and rumors. There are further proposals to improve and scale up the collider. According to CERN experts, collisions will strike things 10 times quicker than they do currently between 2029 and 2042. The website will also be modified to improve exploration and learning. This is fascinating, and you can't help but wonder what kinds of discoveries these scientists may uncover. Or, on the other hand, what global catastrophe this could lead to. Time will tell for the time being. We appreciate you seeing this week's Voyager episode. Click on the video to view more thrilling videos like to this one while you're here.